start with a new session. This is the Lattice signature session. And okay, got it. So the first talk of the session is compressing Lattice hash and sign signatures by Thomas Espito, Mehdi Tibushi, Alexandre Wallet, and Yang Yu. And Thomas will give the talk.
Can you hear me? Yeah. Thank you, Daniel, for the introduction. I'm very happy to be in crypto this year to present you this result we get quite recently. So yes, okay. So first and foremost, let me give you a bit of context and explain you what kind of signatures we can find in the world in 2022. So in this little panorama of signatures, I will draw big circles, which area corresponds to the size of the signatures themselves. So let's start with the hash-based family. So Picnic, Sphinx Plus, and XMMS. Then the Lattice code one, so Dilithium, Falcon, and Wave. And as a reference, like the non-post-quantum one, so RSA and ECDSA on Edward curves. And the aim of this talk will be to take the hash and sign candidates, so Falcon, and see how we can reduce the size of the Falcon signature and more generally of hash and sign type for basically free. Okay, so as I said, Falcon is a lattice-based hash and sign signature. So let me just give you a bit of background on lattices, even though I suppose that most of you are very familiar with that. So a lattice is a discrete subgroup of Rn. So we have this bunch of points which are very regularly spaced in our ambient space. And we can describe a lattice by one of its bases. So think in terms of linear algebra, it will be sets of linearly independent vectors that will span our lattice with integral linear combination. So here it's a bad basis, like long vectors, bad orthogonality defect. But we have also good bases. So short vectors, almost orthogonal. We're happy with that. Okay. And like first motto about lattices is like finding short vectors in a lattice is a hard problem. This quote comes from Aitai in 98. And second motto you should remember is this one, that the better my base is, the easier my problem becomes. And basically, apocryphal citation from every lattice cryptographer ever. So just remember that for the rest of the talk. Okay, so I was speaking of signatures. So let's see now how to sign and what we can say a bit about that. Okay, so this framework is a so-called GPV framework from Guthrie, Pikert, and Baikutanethan from 2008. So it's a hash and sign based paradigm. So how do we sign? We take our preferred lattice. So here it's something which is here the hexagonal lattice. That's my favorite one. And to sign, what will I do is first I will hash my message somewhere around the lattice. So here my hash is here. As you can see, it's not a lattice point. It's somewhere around. Okay. Then I will do a discrete Gaussian sample around centered at this hash. So, okay. Please do my Gaussian sample. Okay, nice. So I have like I drawn the density here. So darker, the higher the probability. So I will sample my lattice point, and I will use for that the secret key, which will be a good basis. I will come a bit on that later. So I have my sample, and now my signature will simply be this difference vector here. It's a short vector. I'm pretty happy with that. Okay. So this was for the signing. Now, how do I verify it? So I start with my signature. I will first verify that the signature itself is small enough for a certain bound that will depend on the parameters and will be set by security. And then I will verify, like, let's say, the functional equation, which is basically saying that S minus a hash lies in L, because as you remember, my V here was a lattice point by definition of Gaussian sampling. Okay. And then if these two conditions are verified, I will accept. Okay. So now a bit on security. First of all, the key recoveries, which consist in finding the secret key from the sole knowledge of the public key. So my public key here will be any lattice basis, and my secret key, as I said, will be a good one. So this amount to do some lattice reduction, or like which amounts itself to solve SVP problem or approx SVP. We will start from an arbitrary basis, and we will like reduce it until we find a good one. So here it's just the case in dimension 2. Gauss algorithm, it's pretty easy. Okay, however, we want it to be hard. So to make this problem hard, we need to work in large dimension, of course, and we want the public basis to be bad in some sense, because of course, if I give you a good basis to begin with, you don't have anything to do. Okay, so that's first the key recovery. And the second property we want to enforce is the forgery. So the forgery amounts to find a lattice point which is close to the hash, because as you saw, the first step of the verification was to check that my signature is small. So it's an approx CVP instance, which means that I want to find a lattice point close to a certain target. And like, as I said, like the motto is that the better the basis, easier my problem becomes in lattice reduction. So to have this problem to be hard, I need the distance between the guaranteed distance I want to solve approx CVP must be small. So it means that the Gaussian sample I'm doing to sign should be small as well. And if it's small, since doing good Gaussian sample is a hard problem, I want my private basis to be good in some sense. So having short vectors, having very particular properties with regards to lattice reduction, to Gaussian sampling, sorry. Okay, so that was for the security. So in a nutshell, what I need is a good enough private basis and whatever bad public basis. Okay. So now to enhance a bit and get better, smaller signatures, we will not instantiate this GPV framework on an arbitrary lattice, but we will instantiate it on nice enough lattices, and in particular on n-true lattices. So what are n-true? N-true is a rank 2 lattice over some ring, which can be written as follows. So it's a parity check lattice. I have an element h of the ring. I will explain later how it's constructed. And that's a set of vectors uv with u and v in the ring, such that uv inner product with h minus 1 is equal to 0 mod q. Okay. So I have actually a very naive basis that will be a public one of the n-true lattice. It's the 1h0q, because you can check that 1h inner product with h minus 1 is 0, so it's 0 mod q. And that 0q times h minus 1 is q, so it's 0 mod q as well. So you can prove that this is a full basis of my n-true lattice, but it's actually pretty bad in terms of quality. How do I construct otherwise a good basis, the one that we'll use to sign? So actually, I will do it backwards. I will start by constructing the first vector of my to-be good basis. So let's take f and j, which is a small vector with f and j in the ring. And then I will set h to be j over f mod q. Okay, so now like, oh, why I'm doing that? And the answer is pretty simple, because this is perfectly equivalent to having hf equal to j mod q. And then you're like, oh, that's great, because it means that by construction, this f and j belongs to the gamma perp h. So right now, I'm pretty happy. I've done half of the work. And now remember that since I know this public basis here, I can easily see that the determinant is q. So the determinant of my lattice is q. Since it's an invariant of the lattice, I should have also a basis, a short basis, which determinant is q. So my goal now is to find square and triangle in the lattice, in the ring, sorry, such that the determinant of this is equal to q. So I just do undergrad linear algebra here, and I want to solve f triangle minus g square equal q in the ring. Okay. This should remind you of your arithmetic 101 class, and this is called a Bézout equation when you are over the integers, and we know how to solve that. We basically do extended Euclidean algorithm. Interestingly enough, on nice enough rings, we can do a variant of Euclidean algorithm, generalized one, which works pretty efficiently if you are working over a tower of fields. So in wall generality, if the ring is nice enough, we have a very nice way to generate this n-true basis. Okay, so just a bit of example in dimension 2. So which means that I'm looking at the n-true base over the integers z. So I'm taking f equal to 2, g equal to 3, q equal to 7, because whatever, 7 is a prime. If you do the computation, you get that h is j over f mod 7 is 5. And as such, you can construct this public key set. So 1h, 0q, which gives you, as I said, a bad basis. Now you can construct the secret basis using the Euclidean algorithm, as I said, and you get a nicely shaped basis. Okay, that's my secret one. Okay, now let's see what we can do with this lattice. And in particular, we can look at the slices of the lattice according to the vector 0q. So we're looking at all the cosets by 0q, and we give like all this nice slice of lattice. Okay. Why are we doing that? It's because if I restrict these slices to the square of size q, so it's minus q over 2, minus q over 2, q over 2, q over 2, I have an interesting property here. In each of my slice here, I only have one lattice point. Okay, why is it interesting? It's because it means that if I'm restricting to vectors here, I can I can restrict it to these people probably, but if possible, I would like to
My apologies. Please continue. I didn't realize it would pop up anything. I'm just helping out a speaker.
Or is it whatever? Can I get rid of them? Sorry about that. Yeah, that's okay. I mean, the interesting thing is happening behind, like.
Is there anything I can do on my end? I'm really sorry.
Yay. I don't have to start all over again. Good.
Yeah,
it's okay. Thank you. So what was I saying? Yeah, we have a very interesting property in the square. So if I look at each slice, I only have one lattice point in each of the slices. Why is it interesting? It means that in terms of representation, I can only represent my lattice points here by their x coordinate. If I project everyone, I just need to know that, for instance, to represent that point, I just need to know this coordinate. That's pretty good because it means that I need half of the space that I would normally need to represent these points. So let's go back to signatures. And like now we can just take our very nice intro lattice instead of the random one I choose. And we will do everything within this nice square. So, okay, I'm doing the hash of the message. I'm doing my Gaussian sample. We get this vector v, and I will let it go down if it wants, please. Thank you. I will look at it here, and I have these signatures, which is this point here. Okay, very nice. And I will do what I just said. I'm in the slice, so I will just represent it by its x coordinates. Very good. Why is it sufficient? Because now if I take this half signature, I can reconstruct the full signature from that by actually selecting the slice where I was supposed to work in. So I have a unique lattice point here. I take my hash here and I look at it mod q. So I'm inside the cube. And I look at the difference between the two. And surprise, surprise, it's a signature. So it's sufficient to have the knowledge of this x coordinate to be able to reconstruct the signature. So once we've done that, we just do the same. We check that the signature is reconstructed signature is small enough, and we're happy with that. And if then this condition is asserted, we accept the signature. Okay, So that was for the rationale somehow of Falcone, this hash and sign on n-true lattices. So now we want to go beyond that. Like halving the signature was not enough for us, and we wanted to get even smaller ones. So what can we do? So right now we're working in this cube of mod Q cubes, and we are doing some Gaussian sampling, but it's an isotropic one. It's we don't have a preferred direction. We're doing spherical sampling. Okay, so as you saw, my signature will be points on this line. So if I want shorter signatures, I want to favorize points which will be close to the origin. Okay, a way of doing that is to stop sampling in any direction and to favorize the points which are closer to the origin. So basically, I will sample with an elliptic Gaussian, which has now a favored direction, and the direction will be the y-axis. So an alternative way of looking at this elliptic sampling is actually to do some spherical sampling, but in an unbalanced lattice. So how we do that? Basically, we start with our lattice and we say, okay, let's have more points on the y-axis. But if I want to still work with this n-true lattice and this nice mod Q property, I need to preserve my determinant, because if I squeeze my lattice by 2, I have two times more lattice points. My determinant is also multiplied by 2, is divided by 2. So I also need to expand it in the x direction. So now that I divided by 2, multiply by 2, I'm basically still working with the same determinant. And if I do that, I can take my nice mod Q square, but it's not a square anymore, it's a rectangle. And as you can see, I have like a higher density of points on the slices. So now I can do, once again, my spherical isotropic sampling, but I will favorize more points on the slices which are closer to the origin. So I'm happy with that. So what I did actually was to did some distortion on each axis. So I'm actually looking at the lattice under this new norm. So I can do that in word generative for arbitrary gamma, not necessarily 2. And I will just work in this new norm indexed by gamma. So the algebraic part, the functional part, is exactly the same. It's still an n-true lattice, so this lambda per h. The equation is still the same. H is still j over f mod q. Everything works exactly similarly for the algebraic part, but the metric under which I'm looking at the lattice has changed. So basically, the way I'm embedding my lattice points in the R to the n space is different. So why is it interesting? Because it means that I can use that straightforwardly in my hash and sign construction. I just replace everything by doing my operation in the new norm. And since it's still a Euclidean norm, everything remains the same. The discrete Gaussian sampling algorithm will be exactly the same. It's just the quantities will have these gammas there and there. And the assert that S is small will just be done in this new norm. So it's a very easy computation as well. So nothing is really changing. Okay. It was a neat idea, and it's quite simple, but we can be even more simple. And you're like, oh, Thomas, what if actually I'm doing something very stupid? What if I'm just saying, oh, everything is uniform mod Q, like all my quantities depends of Q. What if I just like take a small Q? So you're like, oh, okay, let's do it. For instance, here it was my previous lattice, so the n-true with Q7, and I can do the same, but with Q equal 5. Of course, H is changing because the modular equation is changing, or I can do for Q equal 3. Okay, things start to degenerate a bit. That's a hint that maybe some tricks must be found. But as you can see, if my Q is smaller, of course, I will only choose points between minus Q over 2 and Q over 2. So I'm pretty happy because it's indeed smaller. So it's kind of for free. So it could be like, oh, is it a free lunch here? Like, can I just reduce everything for absolutely free? Okay, of course, the answer is a big no. Like, you never have free lunch theorem in computer science. So why it's not a free lunch theorem? Okay, for the small Q thing, we reduce things uniformly with regards to Q. So in particular, we reduce the size of this secret vector Fj. So for reasons which are linked to the way you want to sample and to have a good basis to sample, you want Fnj to be of size root Q. Okay, so it means that if Q is getting smaller, root Q is getting smaller, so this is getting smaller. So If now it's very small compared to the dimension, then the vector will start to become sparse. It means that we have a lot of zero which are going to appear. I mean, if I have a vector which all coefficients which are non-zero, of course, the norm of the vector should be greater than n, I mean root n. So if I'm smaller than root n, strange things happen. And it's pretty bad because we can have a bunch of combinatorial attacks. In particular, if you think of the very degenerate case where, let's say, the norm of that is root 2, which means that we have two non-zero coefficients. Two non-zero coefficients in dimension n is basically, oh, I will just guess where they are and I will test, and I will just have a quadratic number of tests, so it's a polynomial attack. So we need to be careful. We can't be too small because of this reason. For the distortion thing, where we're unbalancing the lattice, we are actually also changing the norm of AJ because we are looking at it under this gamma norm. Okay, so f will be gamma times smaller and j will be gamma times larger. So for very small f, it will become sparse again for exactly the same reason. And we're not very happy with that neither, because what we can do is exactly what I just said for this very degenerate root 2 case. We can guess the position of the zeros. So here in whitish, suppose that I have the zeros, I guess them correctly, and what I will do is I will just suppress them from the lattice, and I will have a lattice of smaller dimension, and I can apply lattice reduction over the public basis to recover this reduced fj. So the complexity of the attack is then the probability of making a right guess multiplied by the probability or the complexity of lattice reduction in smaller dimension. It's an attack. You can go even further than that. If f is very small, then k is small in the equation h is equal to g f minus 1 plus kq. So by construction, I said that h was g over f mod q. So it means that we have a coefficient k such that h is equal to that. This number of modular reduction mod q we are doing. So what we can do, since this is also small, is to recover the extended vector fj and this k, and we can recover it by doing lattice reduction in 1h0q, the public basis here, extended with 0, 1. And we can combine that with the guessing thing I just explained. So in practice, what does this give? Question. So we have a different regime and different corresponding attacks. So when both f and j are sparse, which means like this very small q technique, we will basically use this recovery of f, j, and k, and we will combine that with the guessing. So we're guessing the position of zeros, suppressing the correct guess from the lattice, and doing lattice reduction in smaller dimension. Then we have this large distortion setting where f is sparse and j is large, and we basically will apply the same technique. And at one point for medium distortion, f is small but not sparse, and j will be large. And we will just, k will become too big, so the attack will not be as efficient, and we'll only do the basic recovery with lattice reduction. And then we go to the standard regime, and only lattice reduction applies. So Duca and Postelwaiter has sent me an email recently that they might have found a new attack in the extreme small q, which is better than this recovery plus enumeration and guessing, which is quite different because it exploits the shape of Bikisi reduced of QR lattices. So this must be tested a bit more, but it only affects the extremal cases. So for a bit of practical things, so you can see here a graph of the security with regards to the unbalancing factor gamma we have here. Gamma equal 1 is no distortion, no unbalancing at all. For small gamma, we are in this pointed small dots regime, which will be the first regime I explained, just lattice reduction. And at one point, we'll do this recovery of fjk. So we have a phase transition around gamma equal 5 in dimension 512 and 124. So for the small q regime, we'll have a curve which is a bit steeper, but actually, if you look at the scale, it's a very small loss. So you start from a big q over here, and if you just say, oh, I can reduce from q equal 140 to, let's say, 100, you're making barely any loss in security. So concretely, what do we have on Falcon 512? So NIST level 1, we start from a signature size, which is the number of the beast, and then we can reduce it with small q. Here I chose 31 to 490 bytes of size. Interestingly, if I'm reducing Q, I'm also reducing the key size. So for certain applications, it can be very interesting to reduce both the SIG size and the key size. And for the distortion, we can reach signatures of 410 bytes. And as you can see, the security is barely affected. So same goes for Falcon and NIST level 5. So if I redraw my little boss from the beginning, we go from something here, which was 66 bytes to 410, and from the Falcon 5, which was 1280 bytes to 780. So that's substantial shrink, so around 30–40%. It also applies to the variant of Falcon we presented at Eurocrypt in 2022, so Mitaka, where we start from a SIG size from 710 bytes, and we can reduce it using exactly the same technique to 460 bytes, and same for Mitaka level 5. So thank you for your attention, and I'm very happy to answer questions if you have them.
Perhaps in the interest of time, we should take the questions offline, but please, yeah, ask one question.
Thank you.
So I like.
Yeah, sure.
The offer to show signatures.
Yes.
But from the point of this mic is okay. Okay. From the point of performance.
Of performance, yeah.
So I think your implementation takes more overhead than Falcon or Mitaka.
So it actually depends. So if we're changing the queue, using a queue which is not this very nice queue where we have the splits for the entity for using the entity, we won't be able to use entity, of course. So depending on the application, we might have not have the same tricks of implementation. But if you're, for instance, not using this nice queue from the beginning, like 9551, it will not change anything basically, because so we did not implement that, so we don't know the exact change we have on efficiency. But for instance, since we are also reducing everything, including the size of the object we're manipulating, the operations are slightly faster as well. So it's kind of complicated to have a definitive answer on which one is the fastest. It really depends on specific parameter sets. Yeah, depending on the parameters you want, it might be faster, it might be slightly slower, but it's very marginal. And the whole thing is on the same range of efficiency.
One more thing.
Yes.
So how about countermeasure against side channel attacks?
Thank you. So that's a very interesting question. So we're actually not changing the rationale of Falcon here. We're just changing parameters somehow. So Falcon will be as hard as Protect, but since Mitaka was actually designed to be easily masked, all these nice masking properties are really remaining unchanged. So it's really as easy as protecting the base scheme. No, not changing anything at all.
Thank you.
Again. And yeah, we can move to the next presentation when they get ready. Yeah, so next speaker is Akira Takahashi. They will be talking about lattice-based multi-signatures with single round online face, work with Cecilia Boschini and Mediti Bushi. And Akira will give the talk.
Okay, thanks for the introduction. Yes, so this is a joint work with Cecilia Boschini from Technion and Reichman University in Israel, and Mediti Bushi from NTT in Japan. So let's get started. So what is a mode signature? So mode signature is essentially a generalized version of the use of signature scheme, where there are multiple signers holding individually generated secret signing keys. So we consider in this work the interactive version of the mode signature. So this means that parties interact with each other and then eventually output a single signature on the same message M. So the verifier takes message signature and the list of public keys that participated in the signing operation and eventually outputs reject or accept. So this is the basic syntax. So what about the security? So usually the security of the mode signature is defined using a game between an attacker and the honest signer. So we usually assume that the attacker corrupts all but one parties. So this means that the attacker can query the honest signer with arbitrary message and dynamically chosen list of public keys. Then after some interaction, attacker obtains the signature, and then later outputs message, signature, and list of public keys. So the winning condition of the attacker can be stated as follows. The attacker wins as long as the output signature message list is valid, the list contains the honest party's public keys, and message list pair has not been queried so far. Okay. So one important difference with the user signature scheme is that because now we are in the interactive setting, we have to assume that attacker can concurrently query the signing protocol. Okay. Because, for example, attacker can start a new signing session without finishing the ongoing signing session with the honest signer. So this is the security goal. So in this work, we'd like to construct a lattice-based mode signature. Our starting point is a user Schnorr-based identification scheme in the discrete log setting. So let's recall that in the Schnorr setting, prover commits to the randomness, and upon receiving some challenge, prover responds with some value Z. And then the verifier checks this basic linear equation. So once you have Schnorr, it is well known that you can instantiate a similar identification scheme using lattices, which is often referred to as a Fiat-Shamir wizard board, originally proposed by Lubashevsky. So just like Schnorr, first prover commits to the randomness. But this time, the distribution of the randomness is either Gaussian or uniform distribution over some small range. In this work, we consider instantiation in the structured lattices. So the challenge space is a subset of the entire ring. Okay. So one important difference with Schnorr is that because all of the secret key, challenge, and randomness are small, potential distribution of the response value Z is also small. And then also it's not independent of the secret key. So this means that the prover cannot reveal the response directly. Additionally, the prover has to perform the so-called rejection sampling. Then after rejection sampling, the verifier checks a similar linear equation. Also, because the norm of the vector Z is somewhat small, the verifier has to check that norm is smaller than the certain bound. So once you have a Schnorr-like identification scheme, we can naively construct the two-round protocols in a passively secure setting. So this is relatively simple. Essentially, we ask each signer to produce locally a Schnorr signature. So each signer first commits to the randomness, and then upon receiving the other party's commitment, you take the sum of the commitments. And then you derive the joint challenge, and then later exchange the response values. It is well known that using the existing technique, you can actually aggregate the public keys. So for example, you can take a single public key that looks like a single Schnorr-like public key. And this single subpublic key can be constructed through the random oracle. So more concretely, you can generate random coefficient through the random oracle and then take the linear combination. So again, exploiting the similarity between Schnorr and Fiat-Shamir wizard board, we can directly translate this protocol into the lattice-based one. So syntax is mostly the same, but one difference is that, of course, you have to perform rejection sampling. Also, the key aggregation can be done in a similar manner, but we use random coefficient from the challenge space. Okay. So this works thanks to essentially the homomorphism of the sys function here. Okay, so there are already few differences. So for example, as I said, typically the distribution of randomness follows Gaussian or uniform distribution over some small range. So if it's instantiated with Gaussian, because the sum of the Gaussian follows again Gaussian, eventually the verification bound has to be adjusted. Basically, we assume that the resulting response value follows Gaussian with slightly expanded Gaussian parameter. Okay, so also because we have to wait for all the parties to pass the rejection sampling simultaneously, in order to minimize the number of rejection, you either have to increase the Gaussian parameter accordingly or perform parallel repetition so that you can pick one instance where all signers pass at the same time. So this is a basic blueprint, but it is well known that this naive construction is insecure whenever the attacker behaves maliciously. So in the discrete log setting, actually the existing two-round Schnorr-based protocols are insecure against concurrent attacks. For example, the drivers et al. Show the attack exploiting the K-list sum problem. And there's even more efficient attack using ROS problem. So in order to achieve active security, we have to do something more complicated. In the discrete log setting, there have been several interesting techniques. So for example, the most natural solution is a commit and open. So with this solution, first you commit to the U value, and then upon receiving the other party's commitment, you open the commitment. So this works nicely, but unfortunately, it requires 3 rounds of interaction. It adds to the round complexity. So in order to preserve the round complexity, there's another method called trapdoor homomorphic commitment. So here, you first generate a commitment key based on the message to be signed. And then you send a commitment to the U value. Because now we instantiate the commitment with additively homomorphic one, you can take the commitment, you can take the sum of the commitment in a meaningful way. And if you additionally equip the commitment with a trapdoor, the simulator can equivocate the commitment to whatever value. And it turns out that this allows you to simulate even with the 2-round protocol. However, one drawback of this method is that because the commitment key depends on the message to be signed, 2 rounds of interaction must happen online. You have to first see the message and then perform 2 rounds of interaction. So there's more interesting method, which uses linear combinations. So in this method, you first exchange a bunch of U values. And then upon receiving all U values, you take the random linear combinations. And how random linear combination coefficients are derived will be explained later. So this is nice because the first round interaction can be essentially performed offline. So this leads to single round online phase. So let's zoom out a bit and briefly recap the existing constructions. So actually using the existing method, commit and open trapdoor homomorphic commitments, you can instantiate 3-round and 2-round protocols, both in discrete log and lattice settings. So here's a typical way to translate the Schnorr-based protocol to the Fiat-Shamir wizard board. So first, you take the Schnorr-based protocol and then replace all the discrete log-based operations with lattice-based one. So you sort of emulate what's happening in the Schnorr-based protocol using lattices. And typically, as long as the underlying Schnorr-based scheme relies on discrete log-based assumption, the lattice-based counterparts can be also proven secure, assuming the hardness of the SIS program. And the latest constructions on this line of research are MUSIC2 and DWMS, which are presented in Crypto last year. So these constructions are nice because they essentially use this linear combination technique, and they can successfully achieve 1-round online phase. But here's a main technical challenge. Because these constructions rely on either algebraic group model or one more discrete log assumption, it's hard to directly translate this construction into the lattice setting. Of course, in principle, you can consider lattice-based analog of AGM or one more discrete log assumption. But definitely, at the moment, it's not the standard assumption yet. So our question was, can we construct a scheme with single-round online phase from standard LWE and SIS assumptions? In this work, we answer this question by proposing a new scheme, MUSIC. So let's take a look at our scheme. So on a high level, it works as follows. So the main differences with the passively secure protocols are highlighted here. So during the first round of interaction, you exchange a bunch of U vectors. And please notice that this first random interaction is completely independent of the message to be signed. We also assume power of 2 cyclotomic ring here, so everything operates on polynomial ring. And then upon receiving all the U values, message to be signed, you take all of them and hash them. And then eventually you derive the random coefficient B. So if you're familiar with music2, DWMS, or Frost distributed log-based schemes, you probably see a lot of similarities here. But there's one important difference. So this random coefficient B actually follows Gaussian. The reason why B follows Gaussian is going to be clear when I give an overview of security proof. So basically, thanks to this random linear combination, it makes it difficult to predict the resulting U value that is going to be hashed when you apply Fiat-Shamir. And this prevents a concurrent attack, essentially. So this is a very basic two-round, two-party protocol. But you can easily generalize this protocol in the n-party setting. So in the n-party setting, in the paper, we show that the signature size scales logarithmically in the number of parties times the degree of the polynomial. So at the high level, the scheme is relatively simple, but proving security from standard assumption becomes quite intricate. So I would like to give an overview of the security proof. So typically, the main technical challenge of security proof when you for the multi-signature is to simulate the honest signer's behavior without knowing the secret signing key. So there are essentially two key observations. First, we use a generalized version of rejection sampling. This can fix the Gaussian parameter of the potential response value Z. Second, we use pre-image sampling algorithm using a standard lattice trapdoor technique. So using the knowledge of the trapdoor, you can generate the bunch of U vector, and then later this helps you simulate the signing oracle. So let's take a look at each technique. So let's recall the standard rejection sampling from Lubashevsky's paper. So as I said, the potential response value Z somewhat depends on the secret key. So this means that you have to perform some rejection sampling algorithm so that the resulting distribution is centered at 0. So the resulting Z looks completely uniform and completely independent of the secret key. However, in music2, we have to generalize this setting. So as I said, the randomness of the signing algorithm is constructed using the linear combination. So this means that the randomness Z, randomness R, is constructed from smaller Gaussian distribution. However, the resulting output value Z has to be actually independent of the random coefficient B. So the reason why we need to make it independent of the B is that in the security proof, you actually have to generate a Z first, and then only after that, you can generate B. So this requires us to fix the Gaussian parameter. Also, it turns out that the rejection sampling works even if the distribution of the Z is restricted to the lattice coset. I'm not going to the technical details, but this is going to be required during the security proof. So in our paper, we show this generalization of the rejection sampling works. So the second key technique is pre-image sampling using the standard lattice trapdoor. So let's look at the basic operations that often happen in the lattice-based signatures. So you first generate a uniform matrix U, and then take Gaussian vector, output the multiplication between them. So it turns out that if you know the trapdoor for the matrix U, you can do this operation in the opposite direction. So you take the target vector U, and with the knowledge of trapdoor, you can sample the pre-image B, following a Gaussian distribution defined over some coset that satisfies this equation. So given these key techniques, it turns out that we can give a security proof only assuming SIS and LW. So this is the overview of the signing oracle simulation. So in the first random interaction, first parties generate a bunch of U vectors with the known trapdoor, and then output U. Then on receiving the vectors, you run honest verified Zenoid simulator of the underlying identification protocol. And this ensures that honest parties transcript satisfies the verification equation. Then, thanks to the knowledge of trapdoor, now you can sample the pre-image of the coset. So this is exactly why the random coefficient has to follow Gaussian. So this helps actually, this helps us invoke the existing pre-image sampling algorithm. So now you get the vector V, and then program the random algo using the sampled vector V. For example, you can instantiate this algorithm using the well-known Michancho-Piker trapdoor by setting the number of vectors appropriately. So this is the high-level overview. And please notice that this simulation is purely statistical. So in this work, we say the feasibility of Hiatt-Shamir with a boat-based mode signature with single random right phase. And then we can show statistical simulation of sign oracle. And remarkably, during the simulation, we require no one more assumption as in the discrete log setting. And once you have a simulation of the sign oracle, you can invoke the standard forking lemma-based argument. So first, you rewind adversely, and then obtain two forgeries, from which you can construct the C solution. And this reduction is done in the classical random model. And again, we rely on essentially two keys of observation. One, generalized rejection sampling lemma. Two, pre-image sampling technique using a Lattice trapdoor. But this only comes into play in the security proof. The actual signing operation does not require pre-image sampling or trapdoor generation. So as a concurrent work, I would like to mention the squirrel scheme, which also achieves a non-interactive mode signature using lattices. And their scheme completely rely on completely different techniques. So if you're interested in concrete and efficient scheme, I recommend you look at this paper. So in this paper, we mostly focus on feasibility of the one-round online phase using standard assumptions. So efficient instantiation and concrete parameters are left for future work. For example, can we exploit the n-true or one more SIS assumption, which was proposed recently, in order to minimize the overhead introduced by random coefficient technique. And this might help reduce the signature size or communication complexity. Also, the natural question is whether we can give a security reduction in the quantum random. In this work, we rely on the classical random and this forking lemma-based argument. Another important, interesting question is to give a security proof in a simulation-based model. So usually, most signatures security is defined using the game, but since we care so much about the concurrent security, it's probably natural to consider simulation-based security as well. So thank you so much for your attention. If you have any question, I'll be happy to answer.
So we have time for one brief question.
Thank you for the presentation. Any intuition on what you would need to prove strong unforgeability and or security under adaptive corruptions?
Okay, so regarding strong unforgeability in this paper, we didn't really consider strong unforgeability. So I wouldn't guarantee anything about that setting. And I'm not sure about the adaptive corruption because now we are in mode signature setting. The adversely doesn't really move from one party to another to corrupt the parties. So we basically assume that all but one party is already corrupted and honest parties is fixed. So yeah, I'm not sure how you define adaptive security in the mode signature setting. That's the answer.
Okay. We can move to the next presentation, will be given online.
Can you hear me on Zoom? Go ahead and share your screen for the next presenter. Thank you.
Hello, let me share my screen. So is everything fine? Can you hear me?
Yes, we can hear you. Your presentation's up on the screen. You're good to go. Thank
Oh,
you.
Perfect.
Okay. So the next presentation is a new framework for more efficient lattice-based partially blind signatures by Shuichi Katsumata and Rafael Del Pino, and Rafael will give the talk.
Thank you. Thank you for the introduction. And so in spite of the complicated title, what we are doing is simply more efficient blind signatures on lattices. So first, what is a blind signature? So we have two parties, a user who has a message and a server who has a signing key. And the user wants to have a signature on his message under the signing key of the server without revealing his message. So we consider only round optimal solutions here, which are solutions in 2 rounds, in which first the user will send a first flow, which we'll call the commitment, and the server will send a response. And finally, the user will output a signature. As per usual, we want correctness, meaning that if the protocol is run honestly, then the user outputs a valid signature. We want unforgeability, and more specifically, one more unforgeability, meaning that if an adversary can observe L sessions of the protocol, it should not be able to publish L+1 signatures afterwards. And blindness, meaning that intuitively what we want is that the server should not be able to link any signature sigma to a specific execution of the protocol, C sigma prime. So that's for what blind signatures are. And what we obtain is a more efficient, lattice-based, round optimal, meaning in 2 rounds, partially blind signature. So partially means that we can add any fixed message to the blind message. And that's useful for authentication, anonymous credential, and other constructions. And we obtain all of this in the QROM. So how do we do this? At a high level, we use the generic blind signature construction of Fishling 2005, which needs a commitment, a signature scheme, and a zero knowledge proof. So for the commitment, we will just use the BDLOP commitment, which is one, I would say, most used in lattice-based cryptography. And for the signature and zero knowledge proof, we will need a new approach because things don't just work easily when trying to do Fishling on lattices. So in fact, there have been a lot of works on trying to do blind signatures on lattices, and all of them have some caveats. So a first line of work was started by Ruckert in 2010, and the last paper being by Hauke et al. In 2020. And the problem of this line of work, which is based on the Schnorr type blind signature, is that the first few papers had a wrong proof of security. So the Hauke et al. Repaired this proof of security at the cost of having a signature that is of several megabytes. So that's an issue. A very recent work by Lubashevsky et al. Uses one-time signature and OR proofs, and it achieves small signatures with round optimal, small and round optimal signatures, but it needs an upper bound on the number of signatures because the running time of the protocol is linear in the total number of signatures. And finally, there have been 2 other recent constructions based on Fishling's generic construction by Agrawal et al. And the first one requires evaluating a random oracle via an FHE. So which, if you think about, is not really possible because a random oracle does not have a circuit. So what they do is they take an explicit circuit of an explicit hash function instead of a random oracle. But even doing this, evaluating such a function with a fully homomorphic encryption is very costly. And the other solution requires a new assumption called one more SIS, which was created ad hoc for this paper, and so has not really been studied apart from the authors of the paper. So how do we compare? So the Hauke et al., as we said, has a very large signature size, which is nearly 2 orders of magnitude larger than other schemes. The Lubashevsky et al. Has a linear signing time in the total number of queries. And the Agrawal et al. Paper uses one more SIS, which is not studied at all. Not that little, but not well studied yet. So how do we compare? Well, we have small signatures, which is in the same ballpark as the two later ones, constant and even short signature times, and only well-studied standard assumptions. And it's worth noting that our signature size is twice the one of Agrawal et al. But as a matter of fact, they use a non-interactive zero-knowledge proof of knowledge that was published after we submitted. And we are quite certain that we can use the same NISIC to obtain an improvement of up to a factor 2. So we could also potentially go down to 50 kilobytes. So in more details, we have round optimal signature, meaning that only 2 rounds are needed, unbounded. And it's worth noting that in this previous slide, the Hauke et al. And all prior works also have technically bounded number of signatures because they are based on the Schnorr type blind signature. And all such constructions are subject to the Ross attack, which only allows for polylogarithmic parallel number of signatures. So we are completely unbounded. So there is no Ross attack on our signature scheme. We are only under standard assumption, being modulo LWE, modulo SIS, and the decisional small matrix ratio, which is another word for just the n-true assumption. And we have quantum realm security. And here it's worth noting that really all the proof have been done in the QROM. And even better than that is that the QROM does not affect our signature size adversarially, meaning that we don't incur any loss going from the ROM to the QROM in signature size. And we are as efficient, if not more efficient than prior works. As I said, we have 100 kilobytes and maybe can go down to even 50 kilobytes. So what is this Fishlin construction I was talking about? So still round optimal, only 2 rounds between a user and a server. And first, the user sends a commitment to his message, which we will call C. The server will sign this commitment under his signing key. And the user will encrypt both the commitment and the signature. And then he will output this ciphertext, a message, and a proof pi. So in itself, this scheme is very simple, and all the complicated part lies in this proof. So what does he want to prove? He wants to prove that he has public information, being the message and the ciphertext, and private information, being the commitment and the signature, such that the ciphertext opens to a pair C sigma, such that the commitment opens to the message M, which is public, and sigma signs the commitment C, which is still private. So that can be represented as a circuit and evaluated in zero knowledge, but that can be very complicated. So what are the issues we have on lattices? Well, the first issue is that in the signatures you have seen before on this session, and basically all signatures that rely on lattices, we use a hash of the message instead of a message, simply because using the message directly, you could use the all zero message and leak information about the signing key in most, if not all, lattice-based signing schemes. So we hash the message before signing for security. And that is a huge issue because, as you remember from the previous slide, we have to prove that sigma is a signature of C. And if we hash C, then now we have to prove that sigma is a signature of the hash of C, which is even more complicated. And as a matter of fact, when I talked about the Agrawal paper et al., which uses FHC on the random oracle, that is what they do. They do prove that sigma is a signature of H of C by using FHC. But we want to avoid that because, well, first, the proof is not very nice, and that incurs a huge cost. And even if we avoid that, there is another problem, is that even without a hash, the relation we have to prove is very complicated. So the signature size is going to be very large anyway. So we have to find a way to prove a simpler relation. And we do this by finding an intricate relation between the commitment and the zero knowledge proof that basically allows us to remove the commitment from the signature and then just obtain a signature directly with very little work. So how do we do this? Well, first I need to present the building blocks. So first we will use the BDLOP commitment by Beau Metal, which is very simple. In fact, the commitment C is separated in two parts, a top part C1 and a bottom part C2, and it's just a tall matrix times a randomness R plus 0 on the top part and a message times a gadget matrix on the bottom part. We don't care at all what the gadget matrix is right now. What we do care about is that we can notice that the top part of this commitment, A times R, does not contain any information on the message. It's just a random matrix times the randomness. All the information on the message is on the bottom part. And as a matter of fact, the binding will use the top part, because if we suppose that we open to two different messages, then we solve an SIS on the top part. And the hiding will use the whole matrix multiplied by the randomness. We will use LWE. But what matters is that the only part of the commitment we need for the server is the bottom part. So what if, wait a minute, first I need to present the signature. So the signature will be a ABB style signature, meaning that we have a public matrix composed of two public matrices, A0, A1, the message M, and the gadget matrix G. And to sign, the signer will sample a small e, such that this matrix times E is equal to a fixed vector U. And to do this, the sampler needs to have M be invertible and to know a relation between A1 and A0. So the matrix is constructed such that A1 is equal to A0 times R0. And using standard techniques, then we can use G as a trapdoor and sample this small vector E. So now what if we want to sample the preimage directly of C2? So in the previous slide, we had a public matrix with M times G, and signing M would be sampling E for this public matrix. Now, what if we sign C2, where here sign is a different notion because we don't have the G matrix, but let's say we can sample E such that A0, A1 plus C2 E is equal to U. Well, first, can we sample it? Well, not really, because we don't have a trapdoor here. We need C2 to be equal to something invertible times the gadget matrix, and we don't have this. But that is easy to fix simply by taking a trapdoor on the A0 part. Because instead of using a trapdoor on A1 and this part, we can just say that the A0 part has a trapdoor, for example, an untrue trapdoor. And now we can sample any matrix E for any A0 concatenated with any matrix. So we can just put a trapdoor in A0 instead of the right part of the matrix, and we can sample. So now we can sample this E, but what is the point of this? So remember that C2 is equal to B times the randomness plus M times the gadget matrix G. Now, what if we replace this in this matrix? Well, we can note that this is nearly an ABB signature because we have A0, we have A1, we have M times G and E, and just B times R that bothers us. But apart from that, we have an ABB signature. And what is really nice is that, well, B, we can just, it's public. So we can just move it to the public matrix and say that it's part of the signing matrix. In fact, when using ABB signature, we can append anything at the right, and we still have a valid signature. So we don't care, we can just move B to the public matrix. And we can move R to the randomness vector because R is small. So if we just push it to the right, we have a new secret vector, which is E1, E2, R times E2, where E1, E2 are the two parts of E. So what do we have? We have a new public matrix and a new private vector, such that this vector is basically an ABB signature for M. And we cannot release this vector E1, E2, or E2 directly as a signature because it is directly correlated to E, so the server would be able to link the signature. But what we can do is just publish a very simple non-interactive zero-knowledge proof for SIS, where we prove that this matrix, which is completely public, times a small vector is equal to U. That is very simple to do. So what is our scheme now? So the user commits to the message, and C1 and C2 is commitment. The server samples E such that A0, A1 plus C2 times E is equal to U, sends E. And the user checks that the relation that I said before is valid, and then outputs just his message and a proof pi, where pi is just a non-interactive zero knowledge proof of knowledge of a small secret E prime, such that this public matrix A0, A1 plus message times GB times E prime is equal to U. And that is very simple and efficient. But we still have a problem. As I said before, we need to hash C, because if we don't hash C, here the user could just send C2 is equal to 0. And then if he sends C2 is equal to 0, then he gets a pre-image of just basically A0, E1, and he gets a lot of information on the trapdoor of A0. So that would be an issue. So we have to hash C, but we really don't want to. So what can we do? Well, we just prove that C is of the form that we said it was. So we do prove that C is a matrix AB times R plus a message times G. And that is enough. In fact, that is enough, but we need some specific zero knowledge. So we need a straight line, extractable, exact, non-interactive zero knowledge proof of knowledge. So what does that mean? So I will only consider Fiat-Shamir type of zero knowledge proof. So in which we send a first transcript, which is the commitment, we get a challenge, and we send a response. So usually when we do Fiat-Shamir type of zero knowledge proof, we have special soundness, meaning that given two transcripts, YCZ and YC prime Z prime, we can extract a witness. But that's not what we want, because having such a property means that we need to rewind the zero knowledge proof to obtain a witness. And since the zero knowledge proof is used as part of another protocol, and in the first flow of another protocol, we cannot do rewinding without incurring exponential loss in security. So we could accept an exponential loss of security, or we can use a straight line non-interactive zero knowledge proof, meaning that given only one transcript and a trapdoor, which is in the common reference string model, we can extract a witness. So this way there is no rewinding, and we can extract witnesses on the fly and finish the proof. Another thing we don't really need, but which is much better, is an exact proof. So what do I mean by exact? So this is a problem that is specific to lattices, being that we want to prove that A times S is equal to T, but the Fiat-Shamir with abort only proves that A times S is equal to C bar times T for some small C bar. And that has been around since 2009 in the Seminar Lubashevsky paper, and has basically always been a part of the picture in lattices. And very recently, we have had a series of work that construct exact proof for this relation. So where we don't have this small C bar. These proofs are somewhat less efficient, but they prove a much stronger relation, which is much better for us because they result in a smaller size of signature. So we have to combine this exact proof with the straight line extractable proof to make a new zero knowledge proof in our paper. So how does it work in the end? We have the previous scheme, which is as described before, and we simply add a proof, which is going to be our straight line exact proof. And the server just verifies this proof pi1 and does the rest of the protocol. And what is really nice is that this proof is larger than non-straight line and not non-extractable proof, but it does not have any impact in the signature because the signature is the message and the proof pi, and the pi1 is just for the server to check. So it's some communication size, but no impact at all on the signature side. So what do we get? As I said, we get a more efficient lattice-based round optimal partially blind signature in the QROM. And so the first thing to be done is to use the new, more efficient exact proofs, but that is in fact not as easy as just plugging them in, because combining exact proof and straight line extractability can be very complicated, and the proofs of security are rather complicated. So that's something we are going to do. And another idea would be to increase the efficiency of this construction through stronger assumptions. So maybe not as strong as one more SIS, but stronger than just standard assumptions. And that's it. Thank you for listening.
So we have time for one brief question. Okay, so I will ask one brief question. So Raphael, so currently there seems to be a big gap between, so the efficiency gap between blind signatures and regular signatures for lattices seems quite a bit bigger than other problems based on a number theory. So is this indeed true? And do you think is this something intrinsic about the difficulty of using lattices, or there is a hope to get the same level of efficiency?
So right now we have a gap because basically we use zero knowledge, and zero knowledge on lattices increase. The more proof and the more complicated you do they are, the more the slack increases, and so the higher the gap becomes. But we are getting better and better proofs, so the gap is reduced by this. And if we use constructions, if we can find some constructions that require less zero knowledge proofs and that are more straightforward, then we can reduce the gap, never to maybe 1:2 or 1:3 ratio.
Okay, so thanks, Raphael.
Thank you.
And it's already almost time for the next session, the award paper session. So please stay here while they get ready for the next session. Oh, sorry, they are telling me that the next session is located in the other room. Okay, so please don't stay here.